A user sends a command, buy CE above 24,000. But when the second command, keep SL50, enters, the system throws a massive error. This happens because base large language models are stateless. They execute in a complete vacuum, retaining zero memory of prior calculations. To maintain logic across multiple queries, you must build a dedicated architectural layer at the front of the pipeline, short-term memory. This layer operates exactly like a computer's RAM. It holds only the most immediate conversational context required for the current task. It is a highly constrained staging area, not a permanent archival database. Regulating exactly what occupies this specific bounding box dictates whether an LLM can successfully execute multi-step logic, or if the entire operation crashes from context loss. This network graph tracks the complete chronological flow. Data routes first into the short-term memory node, acting as the absolute frontline. It filters the active window, while older historical nodes, long-term and vector memory, wait to be queried before funneling into the final LLM node. A frequent error in prompt engineering is treating this active window like an infinitely expanding container. Developers attempt to store the long-tail history of an interaction directly inside the immediate context window. You can see the explicit flaw in this Python snippet. The logic takes the short-term array and explicitly appends the entire history of self.long directly into the immediate payload. This chart maps the mechanical reality. A fixed short-term context forced atop a massive, expanding block of historical data. As the session continues, the long-term array violently breaches the API token limit. The application overloads and crashes. Even before reaching that limit, the system degrades. Packing the payload with historical tokens heavily spikes latency and destroys the signal-to-noise ratio. The model now has to sift through massive blocks of irrelevant conversational history just to locate the parameters for the current step. Its precision drops dramatically. Infinite context concatenation is an architectural anti-pattern. Feeding a model more historical text natively decreases its ability to execute immediate logical tasks. The mechanical solution to context bloat is a state management paradigm known as the sliding window architecture. We initialize a first-in, first-out queue hard-coded to 5 slots. Early conversations fill the memory. When a sixth input exceeds the limit, the array shifts left. The oldest parameter is forcefully purged. The newest seamlessly appends, keeping the total payload size unchanged. This programmatic shifting guarantees a strictly bounded computational load. The context window remains light and highly optimized, whether the session lasts for 10 turns or 1,000. The sliding window ensures that only the most strictly contiguous logic occupies the working RAM, maintaining rapid inference speeds over extended use. While a sliding window prevents basic API crashes, relying entirely on a raw message count is a mathematical risk. Look at these containers. Tracking 5 messages by count causes limits to bulge uncontrollably due to wild length variations. Instead, the right container utilizes token-based windows, filling strictly based on data volume. Capping at 2,000 tokens stops volatility, aligning with API boundaries. Aggressive pruning does introduce a clear vulnerability. If a user states a critical, overarching instruction early in the session, that command will eventually slide out of the window and disappear. To prevent this data loss, developers use context compression. Watch the data blocks on the left slide out of the main array. Instead of deleting them entirely, they pass through a compression funnel and merge into a single, highly dense summary state. This intermediate summarization allows the foundational concepts of the interaction to persist inside the immediate prompt, but at a fraction of their original token cost. For non-negotiable rules, you configure priority memory. Notice the padlock affixed to the data block in slot 2. By explicitly tagging strategic keywords, this parameter bypasses the standard purge mechanism. As blocks cycle out, the pinned instruction remains permanently anchored. Collectively, token bounding, intermediate compression, and priority pinning lock down the volatility of the active prompt without throttling system performance. Returning to the macro architecture graph, the optimized flow is highly stable. The short-term memory node is visibly locked to a fixed size, feeding a smooth, uniform stream of data directly into the final processor. The system enforces a strict division of labor. The pipeline feeds the processor only the precise logical steps required for immediate calculation. Massive historical data is structurally removed from the front lines, routing downward into expansive vector memory databases for asynchronous retrieval. The ultimate scaling law of context engineering relies on this separation. System longevity requires keeping working RAM ruthlessly small, offloading the remainder to the archive. In a production deployment, optimize your context windows strictly for token density, never just for the raw number of message turns. Short-term memory dictates exactly what your model is capable of computing in real time. Defining its precise architectural boundaries guarantees persistent, high-accuracy reasoning across thousands of complex interactions.